So, okay, let's go through GPU computing programmer to have a look how it works. Basically, this is a very simple GPU computing programmer. There is nothing specific, nothing complicated. Basically, this simple program is going to do SAXPY, which means that it's going to do A multiply by vector x. Now we should say it the other way around. Vector x is going to be scaled by A, and then you need to do the addition with another vector y, and you put the result in vector y. This is the math behind this piece of GPU computing code. This is a typical GPU computing code, which is going to run on a system with GPUs as a form factor of PCIe adapters. So we are going to go through this short program to understand how it works with the GPU computing with PCIe adapters. Okay, as I said earlier, a GPU computing program could be divided into two parts. There are the codes that need to be run on the CPU. We call it host code. There are the codes that needs to be run on the GPU. It's called GPU code, or it's called the device code, or it's called kernel code. Basically, it's the same thing. So if we look at this piece of code, we are going to say that here we have the definition of the kernel function. Here is underscore kernel. SAXPY underscore kernel means this is a kernel function. This function is going to be executed on a GPU. Okay. So we start from the starting point, which is the main function for C program. We start to run this program. If you have a server with one socket or two sockets with multiple CPUs, you need to run this code on your server. You are going to launch your code, and you need to use one core to execute your program. And be careful, this code is still not a parallel code. I mean, the host part, the CPU part, is still not a parallel code. It's simply a sequential code. Just here, we are going to call this SAXPY kernel function to offload the workload to the GPUs. Okay. All the other parts are a typical sequential code. Okay. We start running this this code, and we need to calculate some parameters. So we put we give a value to the size, and we give a value to the size space, and then we need to work out this block size, this grid size. This block size and this grid size is used to do the index, the thread grouping. If you come back here, is that you have lots of threads. You need to do the grouping of the threads. Basically, for AMD heap programming, and it's the same thing for GPU CUDA programming. What we are going to do is that we are going to group the threads into warps for AMD. The warp is going to be with 32 threads. And that's the same thing for CUDA. You are going to have a group of threads which contains 32 threads. And this group of 32 threads will be put into blocks. And then the blocks will be organized into a grid. The grid and the block could be two-dimensional or three-dimensional or even one-dimensional. Anyway, you have lots of threads, you need to do the thread grouping. Otherwise, you have hundreds, thousands, or hundreds of thousands, or million threads. You are going to have trouble to manage that. There is a way to organize all these threads. That's thread grouping by using this kind of block grid, etc., etc. And in this piece of code, we can see here that at the beginning, the code has worked out this block size and the grid size, and later on, we are going to use these two parameters to launch the kernel on the GPU. Okay, let's continue. We are going to give the scalar a value, and then we need to declare two vectors, vector x and vector y. Be careful that the vector x and the vector y has been declared, and there are some memory will be located for this vector x and y, and the location will be in the CPU's memory, in the host memory. So x and y will be located in the host memory. And then here is that we need to call some function to fill this vector x and vector y. Okay, we give them the values. Okay, and then because you know that we are going to find out that we need to use the GPU to do this mathematics. But then we know from the previous discussion, we know that the GPU cannot access the memory, the host memory. That means the CPU's memory. That means the GPU cannot access X and Y. That has been declared and allocated in the host memory. So we have to find a way to work with it. So we decided to declare another two variables, which is x and y, but it's d underscore x and d underscore y. D means device. So here means that we need to declare two variables, x and y, which are two vectors. And these two vectors, we intend to allocate some memory from GPU to host this x and y, this dx and dy. So, okay, we have declared dx and dy. We need to allocate the memory for them. What we need to call is that we are going to call heap malloc. Heap malloc means that we are going to allocate a memory, a piece of memory for these two variables, the dx and dy. Right now, we are going to have dx and dy located in GPU, because we know the GPU right now is okay. The GPU can access d underscore x and d underscore y because they are located in the GPU memory. The GPU can access its own memory. That's okay. That's fine. So right now, the GPU can access these two pieces of memory. So that means the GPU can work with this math for this dx and dy. Okay, that's good. But anyway, before we move forward, we have some trouble here. We don't have the value yet because the value has been put in x and y. So what do we need to do? We need to copy x to dx, y to dy. Means that you need to copy the y to dy, and x to dx means you need to copy these two vectors. You need to copy these two vectors from the CPU memory to the GPU memory. And here, these two functions are doing that. You call heap memory copy. The direction of copy is from host, from CPU memory to device to GPU memory, host to device. So you copy them. After the data has been copied into d underscore x and d underscore y, now it's okay. Right now, GPU can work with these two vectors. the GPU can do these mathematics for us. Okay, so if you still remember that we have said that the GPU is good with computing, but it needs the help of the CPU to take care of them. So basically here, all these codes will be run on the CPU. So basically the CPU need to call this function to allocate the memory, to copy the data, and the CPU also need to check the errors. If something wrong happened with the GPU, there is going to be an error message, and it is going to be the CPU to take care of these errors reported for the GPU. So up to now, you know that is the CPU's responsibility to prepare all these things for the GPU. Okay, now the data has been copied into the GPU memory. Now we decided to launch this kernel function call. Okay, SAXPY kernel, this kernel function call, basically what we are going to do is that we are going to call this kernel function, and we are going to pass to this kernel function the dx and the dy. Because this piece of code, this kernel function will be executed on the GPU, and this d underscore x and d underscore y are located in the GPU memory. So that's fine. The GPU can work with these two vectors because the GPU now can access these two vectors. And you pass to this kernel function the scalar a, and the kernel function can work it for you. Okay, fine. But this is kind of a kernel function call a little bit strange, because normally if we call a function, we don't need to have these triple chevrons and the parameters here. But for the kernel function call, we do need to have these triple chevrons. We need to pass to the kernel function call these parameters. Primarily the grid size and the block size, which has been prepared here and here. So block size and the grid size has been prepared. So we are going to pass these parameters to the kernel function call. What's the purpose of these parameters? That's very simple. That's the index grouping. If you remember that the GPU need to do the index grouping and the index, thread grouping and the indexing, and then computation and the synchronization. So this the index thread grouping. Basically, with these two parameters, the kernel function is going to know, oh, okay, you have asked for a number of threads, and you have asked for the threads to be organized in verbs, blocks, and grids. And right now, the kernel function is going to know, okay, you want to have a two-dimensional block, a two-dimensional grid, and in each dimension you want to have how many blocks, etc., etc. These parameters is going to be passed to the kernel function call by these parameters. Okay. And then right now we come to the kernel function. It has been called, and then right now it's time to start the execution of the kernel function on the GPUs. Okay, let's continue. Let's have a look at this kernel function. Before we dive into this kernel function, we need to understand that we have just talked about the PCIe link between the CPU and the GPU is the bottleneck. And here, but we have to work with that. But here is that the fact is that the GPU cannot access the CPU memory. You have to copy the data from the CPU to the GPU, and the data has to go through this PCIe link and be put into this GPU memory. And you know the slowest link for the whole system is the PCIe. And you offload your workload from CPU to the GPU. Offloading of the workload most of the time means transfer data from the CPU to the GPU because the workload most of the time is associated with the data. So there is some kind of overhead for transferring the data from the CPU to the GPU. We are going to find out later on there is also the data transfer back to the CPU because the result will be put in dy and you want to have this final result in the vector y, which is located in the CPU memory. So that means finally you need to copy the result back to the CPU memory, and this copy back is going to be going through this PCIe link. And we know this PCIe link is bottleneck. So you need to spend again the overhead to have the data back. So data goes to the GPU, data comes out from GPU, goes back to the CPU. These are the overhead you have to pay. After you have paid the overhead, you really want to make the GPU running fast, because otherwise the overhead won't worth it. You have to make sure that the overhead worth it. That means you have to make sure the GPU is going to run the computation very fast. So to have this GPU do the computation very fast, the solution is that you have to have enough threads. You have to have enough threads to work on the data you have transferred to the GPU and make things fast. If you use just one thread, you need to have 1 million seconds. If you can have 1 million threads, you just need to use 1 second to finish the calculation. That means you can make things 1 million times faster. This is the trade-off. Because the overhead, you have to make sure you have enough parallelism, and you are going to fully explore this kind of parallelism to make things faster. Let's have a look how we are going to make that happen. Okay, here let's suppose we are going to work with 2 vectors. The first vector, dx, is a very long vector and it has 1 million elements. So we have 1 million elements. We suppose that we have 1 million decimal million elements. So the last one will be 1 million decimal million minus 1, the last element. And then the same time, the y is going to be also 1 million elements. Okay, 1 million elements. Okay, and this is going to be y 1 million decimal elements minus 1. This is the last element. What we need to do is that we need to put this dy here, and what we are going to do is we are going to do that. Okay, now you have 1 million elements in each vector. What we are going to basically, we are going to ask the GPU to give me 1 million threads to work on these 1 million elements. That means I'm going to ask each thread to work on only 1 element. And if you have only 1 thread, that means you need to loop over this 1 million elements. If you need to spend 1 second to finish the calculation, that means for these 1 million elements, you need to use 1 milliseconds to finish your calculation. If I can have 1 million elements, 1 million threads, and each thread is going to work on only 1 element. If you still need 1 second to finish the calculation of 1 element, that means finally by using 1 million threads, you are going to finish your computation in just 1 second. So one thread with 1 million seconds, 1 million threads with just 1 second. And if you look at this wall time, I mean the time you spend with the GPU, you are going to be 1 million times faster. And this means you speed up your calculation a lot, and you are going to gain the time, and this is going to make your data transfer overhead worth it. So let's have a look how it works here. Okay, suppose that what we are going to do is that we are going to ask the system to give us 1 million elements. But be careful is that we are going to have 124 by 124 threads. That's 1 million, one binary million threads. Because for the GPU, the threads are in the group of 32. So if you ask for the threads, you are going to have 1 million binary million threads. But suppose that your vector is decimal million, is 1000 by 1000. That's you have 1 million, one decimal million elements in each vector. Okay, so you have asked for 1 binary million elements. The threads will be grouped like this. In a group, you are going to have the position of the thread, and then the thread will be in a block. The thread will be in a dimension. Okay, and then by using these three parameters, you are going to locate. You could locate a thread in the grouping, in the thread grouping. Okay, so but anyway, there is a small difficulty here is that I have my my vectors organized linearly because I have a one-dimensional vector and it's linear, and you have got these threads organized into two-dimensional blocks, etc., etc. So I need to find a way to tell the threads which element they need to work on. So we are going to pass to the second task, which is the indexing. So let's have a look how it's going to be done. With the position of the thread in the grouping, we can use this formula to calculate the thread ID, the global thread ID. So you have your threads grouped into warps and then into blocks, grids, etc., etc. They have a position in a dimension. And but I want them to work on my linear vectors. So what I'm going to do, I'm going to ask each thread to work out its own ID. Just to remember that here we launch this SAXPY kernel function. We ask the GPU to give us 1 binary million threads. And these 1 million binary threads, they are going to calculate their own global ID at the same time. Every thread will be doing the same calculation at the same time. Now, these threads. So all these threads, all the 1 binary million threads, they are going to calculate their global ID. And then finally, each thread is going to find out its ID as 0, as 1, as 2, as 3, etc., etc., etc. And the last one will be 1 binary million minus 1. The last thread is going to be with this one. Okay, and then what I'm going to do is that I'm going to ask the 1 million threads, each one to work only on one element. I'm going to ask thread 0 to work on element 0. Basically, I'm going to ask thread 0 to do the A multiply D d underscore x0 and plus d underscore y0 and put this value here. This is the thread 0 is going to be doing, and thread 1 is going to be do the same thing. It's going to use a and multiply the second element of this vector and add with this second element of this y-actor and put this result here. And then etc. etc. The second thread will be working on this one. And then just remember here the size is the size of the vector. Okay, so if your thread ID is smaller than the size, then you need to work on an element. That means the last thread that's going to work on an element is the 1 decimal millionth minus 1 element. And this one is going to work on this element, scale this element, and make the sum with this one, and put this result here. And this one will be 1 decimal millionth atom here. Okay. And then there are the threads whose global ID is equals size or bigger to size. And these elements, because we have 1 decimal million elements, but you have 1 binary million threads. So there are some threads, they don't need to work. They have nothing to work on. So that here, it means if your thread ID is greater than 1 decimal millionth, then you have nothing to work on. So that means you need to do nothing. Only these from 0 to the 1 millionth elements, 1 to the 1 decimal millionth elements, they need to work on the elements and put the result. So this line of the code is saying that if your thread ID is from 0 to 1 decimal millionth, so each thread, you are going to look for the element of the vector according to your ID, your global ID, and then you work on the element, and then you put the result in the destination you need to put, which is the memory position, which is holding the vector y in the GPU memory. So that's device underscore y. Okay. This is the way how the GPU computing is going to be programmed by the programmer. So you ask enough threads, you make the things fast enough. That makes your data transfer in and transfer out, the overhead is going to be worth it. And then you are going to speed up the things. After this kernel function call has been executed, the 1 million threads will be stopped. I mean, you don't need that anymore. And then you come back, the control will be coming back to the CPU. The CPU will continue. Okay, we just need to point out that this kernel function, you ask the system to give you a lot of threads. Okay, and each thread will be executing the same kernel function. This kind of programming model is called SIMT. So single instruction means each thread will be executing the same kernel function. So single instruction or sim instruction, multiple threads. So you have multiple threads. For our case, we have 1 binary million threads. And these 1 binary million threads, they need to work on different data. And someone will have no data to work on. That's for our case. And this programming model is called a single instruction, multiple threads. This is for GPU, and this word SIMD comes from Nvidia. It's very similar to the SIMD for GPU, well, for CPU. SIMD is single instruction, multiple data. For CPU, it's called single instruction, multiple data. And this is for CPU. And the function units for SIMD for CPU is AVX 512. This is the kernel, the function units in the CPU core, which is called SIMD. But for GPU, this is called SIMD. The two are very similar, but are very similar, but the nature is different. But they are conceptually they are very similar. And Nvidia has started using SIMD as the word to describe this kind of programming model. Okay, so the kernel function call has been done. You have your speed up, and the kernel function has been executed. It's fine. We need to come back to the host part. So the kernel function has been launched. The CPU need to check whether the kernel launch was successful or not. So it's going to call this function heap, get the last error to check whether there is any error or not, whether the GPU has reported any error or not. And this heap check means that I just need to make sure that the kernel launch has been successfully done. Okay, so the job has been done. The speed up has been done. The final result has been put in the vector y in the GPU memory. Now you need to copy the data back from the y vector in the device in the GPU back to the CPU memory, to the host memory. So you need to do this heap memory memory copy. And this time the direction is from device to host. Device means GPU, GPU to host means from GPU to CPU. You need to copy the data back. You have done your kernel function call. And right now, you do need to use the memory you have allocated in the GPU memory, which is dx and dy. You don't need to have that anymore. So what you need to do is that you need to free these two memories, two allocated memories. So you need to call heap free. Heap free means free this memory. And at the same time, the CPU need to do error check. Okay, so we know that this part of the code is doing the clean up, is copying the data back to the CPU, is doing the resource management. Okay, so if we come back to the previous two pages, we know that the CPU need to work on all these for the GPU to make the GPU function correctly, and the GPU, they need to do the thread grouping and the indexing and the computation and the synchronization. So if you look at our example code here, this code and this code is the host code. Is going to be executed on the CPU. They are doing exactly the tasks from 1 to 6 that they need to do for the GPU to work correctly. And this part of the code, the kernel function call, and finally execution of this kernel function is the code that's going to be that has been executed by the GPU to do the computation and all these tasks, thread grouping, indexing, etc., etc. That's this part of the code. So by going through this piece of short code, we understand that for GPU computing, notably for this kind of GPU computing with PCIe adapters, we need to make sure that the data transfer from the CPU to the GPU and back from the GPU to the CPU, the overhead is going to worth it. That means we have to launch our computation on the GPU by having enough threads. The common sense is that for this GPU computing, you need to start with at least 1 million threads to make your data transfer overhead worth it. Otherwise, you cannot compensate for the overhead you spend with the data transfer. So this kind of programming and this kind of thinking of have at least 1 million threads is to cope with the fact that the GPUs are connected to the server and connected to the CPU by the low-speed PCIe links. Okay, so we are going now. We are reaching the end of the code. The last 2 lines of the code is the output of results. Either you print the result on the screen, either you output the result into a file, and then the execution of the program will be ended. Okay, so we have gone through this short sequential code with GPU computing, with GPU kernel function call, which is the offloading of the computation task from the CPU to the GPU. Okay, this piece of code has shown that we have the previous points we have discussed, the low-speed link between CPU and the GPU, and the separation of the tasks for the CPU code and the GPU code. So all this has been shown by this piece of short code. I think I hope I have made this piece of code clear, easy for you to understand. Basically, if we have the chance, if you have the chance, basically what you can do is that you can try to execute this piece of code on a server, on a node, because this piece of code can be compiled and launched and run on a system. Now, this one is heap computing. Heap is heterogeneous interface for programming. Heap programming is the GPU programming for AMD GPU that equals the CUDA programming for Nvidia GPU. But heap is very much similar to the CUDA. So as long as you are not using some kind of features that's available with CUDA but not available with heap, basically your code could be migrated freely from one platform to the other. For our code, if you can replace the keyword heap with CUDA, basically you can compile and run this piece of code on the Nvidia GPU. So this is the fact. I have just used this example from Nvidia from heap to show the things. I hope I have made the things clear, and that's it. Let's have just 5 minutes of rest, and then we continue afterwards.